Hi, this is Dave Savastano, editor of Printed Electronics Now. I'm welcoming you today to today's webinar, bringing 3D printed electronics into mass production, lessons learned. This webinar will describe the use of Optomec's Aerosol Jet 3D printing technology as a mass production solution at LightOn Mobile Mechanical for smartphone antennas, sensors, and other print devices. LightOn Mobile's 2-year journey from idea to mass production provides many valuable lessons that can be used to accelerate deployment of 3D printed electronic technology at other companies within the electronics industry. Electronically functional inks, substrate materials, the printing process and results, environmental testing, and performance of printed devices will be covered. Additionally, we will discuss the motivations for the use of printed electronics as a manufacturing solution. The talk will highlight challenges and lessons learned bringing aerosols into mass production. We are joined today by two speakers, Mike O'Reilly of Optomec and Henrik Johansson of LightOn. Our first speaker today is Mike O'Reilly. He is the Director of Aerosol Jet Product Leader, Optomec. Thank you, Mike.
Thanks, Dave. I appreciate it. And thanks to the audience for taking the time out of your busy schedules to hear about what it takes to bring 3D printed electronics to the factory floor. In the next several minutes, I'm going to provide background information regarding Optomec and LightOn, and I'm going to discuss the basics of Aerosol Jet technology along with high-level overview of its fit in addressing 3D printed electronics challenges. And then I'll turn the presentation over to Henrik Johansson at LightOn, who will walk you through the process LightOn undertook in bringing Aerosol Jet to the production floor. So let me tell you a little bit about Optomec. Optomec is a leader in additive manufacturing with a growing installed customer base. We have a technology-rich portfolio that is well protected by U.S., European, and Chinese patents. We believe in global partnerships that provide complete solutions to our customers. These global partnerships include material vendors, automation partners, service partners, and whoever else is required to make sure that our customers are successful. We have a very experienced and growing staff of additive manufacturing specialists developing, supporting, and servicing our customers. And as you will hear, our technology is providing real production value within several markets, including antenna, sensors, medical devices, and other markets through our evolutionary additive manufacturing solutions. So let me tell you a little bit about LightOn Mobile. LightOn Mobile has over 60,000 employees and a global footprint. LightOn technology offers a wide array of products and services within the technology sector. LightOn Mobile Mechanical is a strategic business group, and that's who is on the phone with me today, of LightOn Technology Corporation, and LightOn Mobile Mechanical is a key Optomec Aerosol Jet customer. LightOn Mobile Mechanical employs over 7,000 people worldwide and has multiple manufacturing units in China and India. And LightOn also has a network of customer service centers spread around the globe providing design through production assistance. We'll hear more about LightOn Mobile Mechanical as we go through the course of this presentation. So let's talk about Aerosol Jet and our capabilities for handling both 2D and 3D printing. Basically, we use an input of fine particle inks or standard paste. The inks can be conductors. They can be silver, platinum, palladium, copper, nickel. Typically, they're in nanoparticle format. Insulators such as dielectrics can be used, semiconductor materials, adhesives, conductive epoxies, biomaterials. Our first production customers were in the biospace. And from that input of materials, we then output very small droplets that enable us to print fine features as small as 10 microns to millimeters in scale, so we can scale up and down depending upon the process parameters we use. And we can do coatings from 50 nanometers on up, depending upon what the customer's requirements are. So thicknesses typically range in the 500 nanometers up to 8 microns in a single pass with our materials. We're a non-contact process. Basically, how our process works is we create these very small droplets We entrain them in a mist stream. Those droplets could be heavily loaded, up to 65% weight percent by volume, heavily loaded, and entrained into a mist stream. Typically, it's a nitrogen carrier gas that moves the material through to our print head. And as the material is passing through our print head, we surround it once again with another nitrogen stream. Basically, think of it as a curtain of air that directs the material down onto the surface of the substrate. And that maintains the fidelity of the material as it's being printed. So what that enables us to do is have a high standoff distance between the surface of the substrate and the nozzle outlet. So that distance can be anywhere between 1 and 5 millimeters, and while we maintain fidelity of that printed feature. Because it's a non-contact process, it easily allows us to print on both 2D and 3D surfaces. There are some key advantages to printed electronics and to the aerosol jet process. We only print material where it needs to go, so there are basically cost benefits to that. We're not wasting, it's not a subtractive, it's only an additive process. There's no plating required. We're printing a functional circuit, so you don't have to then go and do secondary steps like plating. And in many cases, we help to improve end-to-end product performance. A lot of that has to do with our ability to print onto complex shapes that current manufacturing technologies just can't do today. So, due to these capabilities, companies such as LightOn began investigating aerosol jet as a production solution about 3+ years ago, and that led them to start evaluating our technology to address some of their next-generation production challenges. Some of these challenges were driven by substrate. Some of them were driven by customer functionality that customers wanted to add onto the substrate itself, which prevented them from using traditional manufacturing methodologies. And for printing antennas, I just wanted to step through a few minutes on some of the current solutions that are available today that are out there. We'll start from the bottom up. The first is hot foil. Hot foil's been around for many years. Basically, it allows a previously 2D manufactured circuit to be applied to a 3D surface by laying the foil over the 3D part and pressing or transferring the foil onto the part using a heated press. Key challenges with that are accuracy, speed, and feature transfer size. However, it is being used in some applications very successfully today. Another key technology is two-component injection molding, or two-shot. It is a widely used technology for high-volume production of various parts, whether they're molded interconnect device parts, antennas, etc. It basically has the ability to take a molded part that has a circuit on it and basically interface that into a previously created component. So two shots, two components molded together. There's typically a very high initial manufacturing cost in developing a two-shot process. And this is due to the cost of creating the molds, which limits the efficiency of this method for things like small production runs or late-stage design modifications. However, it's a solution that many customers use day in and day out for traditional product manufacturing. Laser direct structuring, or LDS, is really one of the workhorse technologies that's out there today for creating 3D antenna or for creating molded interconnect devices for the automotive world, etc. Laser direct structuring, typically works with doped thermoplastics delivered as an injection molded part. The thermoplastic is activated by a laser, which traces a desired electrical circuit pattern onto the molded part. And then a physical chemical reaction typically is generated by the laser interacting with the part, which forms a metallic nuclei. And these nuclei act as a catalyst for reductive plating, typically copper. Now, once the part has gone through the LDS process, it is sent through an electroplating process, which typically consists of about 10 microns of copper, plating followed by an overplating of 2 to 3 microns of nickel to reduce oxidation of the copper over time. When we look at aerosol jet prints directly on the surface of an injected molded part. which could be constructed out of standard materials such as polycarbonate or PCABS, so less expensive materials. Once the patent has been printed with a conductive ink, it could be silver, it could be copper. It's then fully cured in an oven or using a laser to meet both mechanical and electrical requirements. The components are typically now ready for assembly. There's no need for plating or overplating steps, and the need for specialized plastics is eliminated. So some key advantages to the technology. Just to talk a little bit about Optomec's platforms. So aerosol jet technology is embodied in a wide variety of scalable platforms that are tailored for specific industry needs, whether it's for material research and development, whether it's for research and development and low volume production, or whether it's a scale up to high volume production. Optomec has a series of solutions that that can meet all of those needs. We also work very closely with our customers, as you can see on the right-hand side, and with their automation partners to provide custom solutions to meet their specific manufacturing requirements. So basically, we can embed our aerosol jet printing technology into third-party automation as required. In many cases, customers are asking us to move parts, large parts, where we just don't have the expertise internally inside of Optomec to do that. So it makes more sense to embed our technology into already existing automation. That does two things. It's familiar to existing customers, and it helps reduce the cost of the overall solution. So enough about Optomec. Now I'd like to introduce Henrik Johansson. He's a senior manager at LightOn Mobile Mechanical, who will discuss LightOn's use of aerosol jet production scale solution for manufacturing mobile antenna and sensors. Henrik?
Thank you so much, Mike. Hello, everyone. My name is Henrik Johansson, and I work at LightOn Mobile Mechanical in the R&D organization, and I'm heading up the antenna technology development team. I'm based in our Swedish R&D site. So LightOn Mobile Mechanical are a manufacturing company for mechanics and antennas for the mobile industry. But we also offer solutions for automotive and IoT products. In this session, I will give you a brief introduction of what we are doing and why we have moved into the printed electronics area. I will also talk about the challenges we had to overcome to take printing to a robust production technology, and I will also give you some case examples of things we have been working on in the field of printed antennas. So let's get started. So this is a big picture view of what LightOn antenna is about and what we are doing. We are an antenna partner from concept to design, from prototype to global mass production. We do in-house antenna research and development, and we have 3 full-scale antenna labs around the world. We design antennas mostly for smartphone, tablet, smartwatches, but also other devices. We manufacture standalone antennas, module antennas, and mechanically integrated antennas. So standalone antennas are when the antenna is a separate unit within the device. Module antennas are when the antenna function is integrated with other functionalities such as audio and speaker boxes. Mechanically integrated antenna is clearly the industry trend today. That's when the antenna is integrated in the chassis or the cover of the device. The different antenna categories can be manufactured with different manufacturing technology, such as sheet metal, flex film or FPC, but also LDS, laser direct structuring, which Mike told you about previously. LDS has been the most common three-dimensional antenna manufacturing technology before 3D printing was developed. So, why did we move into printed electronics, and what drivers and requirements do we have from our customers? So the drivers can be summarized in the categories flexibility, speed, cost efficiency, and environmental impact. And here I've listed some typical comments that can come from our customers. They mention things like, we want to decide the antenna location and shape as late as possible in the development cycle. We want to be able to place the antenna basically anywhere and on any substrate. And for optimized performance, we need local variants of the antenna for each market. And during the development, we need local. We want new antenna patterns for new samples and builds very quickly and rapidly. When we ramp up, we go from 0 to peak capacity in a matter of weeks. The cost aspect is always on the top of the agenda for our customers, of course. We don't want any type of product-specific tooling cost, only generic costs. The environmental aspect for the manufacturing is important, and we want to be as green as possible. And of course, to add to this, there is absolutely no compromise on the hard specification for RF performance, mechanical, and reliability tests. This is given in the industry. So any manufacturing technology we use have to meet these drivers, otherwise it's a no-go. And we believe with our 3D direct print technology we are there. And now I will tell you a bit more about this technology. So, LightOn have been working with printed electronics and printed antennas for at least 5 years in development. And after careful evaluation of several different printing methods, the best suited to meet our demands and drivers, we have selected the Aerosol jet printing system from Optomec with a motion system platform from a company, Neotech. The aerosol jet printing technology uses a aerodynamic focusing technology to colliminate the dense mist of silver droplets into a tightly controlled beam, given an excellent line definition. And what is really unique with this technology is its flexibility for variable distance between the print nozzle and the substrate. And this is the key and the enabler for printing on complex 3D surfaces. The manipulation of the part and shaping of the print pattern is done with a motion platform with 4 parallel stations with 5 axes of movement, 3 linear axes as well as 2 rotational axes. This gives the ability to print on all sides of the part in true 3D. And and the 4 parallel station then ensures that we have a high output of the system. Looking back through the development of this technology, we had to overcome a number of challenges, and here I would like to point out some of them. There are a number of ink providers, and we had to develop the one which is best for our application and to secure that ink for high volume availability. For different substrate material, we need to work with the process parameters. There are a number of ink that works well for higher sintering temperature, but for some substrates, such as polycarbonate and PCABS, we can only sinter to about 120 degrees C. And at that temperature, many of the ink fail. We need to ensure the best print quality for line definition, consistent thickness, and the right process speed. And for antenna functionality, we need good conductivity for the sinter trace. The challenge again have been the low temperature resins. The environmental tests are quite harsh for a smartphone application. Each customer having a different set of standards. As example, some customers, the printed antenna needs to survive high humidity and temp cycling between 25 to 55 degrees centigrade in 9 cycles for a total of 6 days, as well as salt solution sprayed directly to the product for 2 hours, and then left in a high humidity for 7 days. And after this test, we check for functionality and adhesion. And of course, very important that we have excellent adhesion between the printed trace and the substrate. This is normally tested with a cross-cut adhesion tape test. So, moving on. Components for smartphone and wearable devices are typically very complex in shape. To get the best antenna performance, the antenna should be placed far out into the corners. And to interconnect the antenna, normally a wraparound design is used. So going over large as well as sharp radius means that print motion speed needs to be optimized in each section to ensure a uniform trace layer with a desired thickness. Sometimes for a molded structure, the surface is not so smooth as you would think. The surface can have pit holes and other surface defects that causes challenges during printing. In this holes and voids, we have seen capillary action happen, and the ink is pulled down into the openings, leaving a very thin conductive layer on the top surface. The quality of the molding and the print process, as well as the ink behavior, is a very important factor. And with our long experience of in-house molding as well as tooling, we are in the right position of getting the best quality substrate for the printing. And this is really needed for this kind of product. Further on the molded structure, there's always parting lines from tooling, and when trays are to be printed over these, it creates challenges. This is especially difficult for an electrical via design. The cone shape the cone shape of the via creates a very sharp edge midway through the part. Tooling mismatch can make the step even bigger, and in mass production over time, the parting line in the tooling can grow, creating a barrier for the ink. The substrate will have different surface energy depending on the plastic type and also from the molding condition and handling. To get the needed printing result, we have to be absolutely sure we have the right wetting of the ink. Effort was spent to optimize the process and to the ink to be sure that we get the uniform wetting in all area of the part. So that was some of the challenges we have been working on and solved. Now if we look at the solutions and the benefit of our technology. We now have a wide variety of inks that suit most of our applications. We can print on a wide range of substrates, common plastic, glass surfaces, ferrites, and even metals. We can print on a fully three-dimensional surface over concave and convex surfaces. We have a high output due to our multi-station setup, also ensuring the best cost competitiveness. Each of our systems today has four print heads. It is a fully in-house technology that can make the finished products in one production cell, also with rapid design changes if needed. It's an additive process and it eliminates the need to plating, making it a very environmental cautious technology. And now I would like to move a bit more in details on some of these areas. So, design flexibility. With design flexibility, we mean the ability to place the antenna or the sensor anywhere in the device. We want to be as less restrictive as we can. Antennas that can be printed far out in the corners enhances the antenna RF performance, giving the device a better signal reception. When we're printing the sensors, we will also need a very narrow line, and with 3DP we can print down to 400 microns today, and we are ongoing development to push that down even further. Design flexibility also gives the customer free hands for plastic resin selection. No additive is needed in the substrate or in the resin, so we can print on flat or curved glass panels, on outer surfaces, and even inside concave undercut areas in the unibody structure. So, speed. Speed is very important, and speed in the development cycle can sometimes on its own be a decision factor for what type of production technology to be used. With LightOn 3DP, we can make samples from scratch in a matter of 1 or 2 days, and for changes in the antenna pattern, it can be done in a matter of hours. Other manufacturing technologies take longer time, and some even includes a tooling modification. Even a rapid manufacturing method such as LDS will have a longer lead time due to the need of chemical plating process, normally located at a different facility. Now cost efficiency. Telecom and mobile business is a very competitive business. Being an additive process, printed antenna cost is driven by tray size. When the smartphones are getting larger, but the antenna size is pretty much the same as before, the competitiveness of 3DP increases. When comparing to LDS, the cost increases when the product size grows larger due to the plating process cost will increase. For applications like small standalone antennas, LDS can sometimes be more competitive, but as 3DP technology matures, we believe this gap will shrink and soon to be removed completely. Further today, most antenna traces are integrated into larger parts already. So, LightOn and our customer puts high value in the environmental sustainability. 3DP technology is generally much greener than other 3D manufacturing processes such as LDS, especially due to the fact that it's printing and not plating based. Nickel, which is used in an LDS process, is an issue both in production and for the consumer due to the increased risk of allergy. And our 3DP process does not contain any nickel in the process. Printing is an additive process, which means minimal process waste. We can print on biodegradable and recyclable resins as well. It minimizes the logistics and transportation impact due to that all the processes can be done in one production cell with minimized product movements. In 2016, 3DP technology won the LightOn Group Award for reduction of waste and lowering the environmental impact. So now I would like to show you some exciting examples of applications we have been working on recently. The first application example is a combined speaker and antenna module for a smartphone. Antenna trace is printed with our 3DP technology, and as you can see in this picture, the trace is applied in three dimensions with 5 sides printing. What makes this application a bit special is that the antenna is printed on the assembly after the speaker and the gasket is assembled. This gives the advantage of late customization. So the speaker module in itself is a generic part that can be kept in the warehouse. But the antenna trace can be local variants for different markets, such as Latin America and Europe. And when the specific order comes for a batch of Latin America antenna variants, we can start the production with a very short lead time. There is a speaker piece inside of the device, and since that is already assembled, LDS cannot be used because the speaker will not survive a plating operation. Next example is printing of a sensor trace. The 3DP process is used to print capacitive sensor and as well the connection traces. The part we are printing on is a structural frame. So the frame is a metal die cast of magnesium that is combined with an insert molded glass-filled polycarbonate. The metal is giving the extra strength needed for a large and thin device. The connection is done through a via hole in the plastic where we are printing from two sides. Printing here is the only option since LDS plating cannot be done due to this metal die cast. Here we have a back cover of a smartphone where we apply the antenna trays on the inside. For the antenna performance, it is beneficial, as I said before, to place the antenna as far out in the corners away from the PCB engine, and this also frees up space for other functions inside the device. All the antennas, main, cellular, MIMO, diversity, GPS, Wi-Fi, and Bluetooth antennas are printed in the same process step here. Antennas are placed on the inside of the undercut area, and it's very difficult to reach. So the variable and several millimeter standoff of this process is essential to make this part. This would be very difficult with any other printing technology than aerosol jet. The cover material is polycarbonate that is colored in bright colors in several different variants. It's a native color, meaning that no painting process is over the plastic afterwards. So again, comparing with LDS, this would be a no-go since the additive in the resin and the chemical plating process will actually damage the appearance of this visual part. So I've shown you some exciting stuff we are doing currently, but of course we don't stop here. We plan to evolve and improve the process and create new applications. Our company's focus for improvement are currently continuous process improvement to reduce the cycle time and to increase the output. In the area of ink conductivity, we see some interesting work being done. Still, we are looking for better inks with higher conductivity, especially for lower sintering temperature below 120 degrees. We are working on sintering technologies, speed and performance. We are also working on printing on new materials. Porous materials seems to be quite difficult, but we are trying to solve that as well. We're also looking into copper-based ink to drive the product cost down even further. We are also developing new exciting applications area to integrate smart functions to new products. Internet of Things is a great business opportunity. All devices connecting to a wireless network needs to have an antenna that can be made with printing to save space. Also, flexible, foldable, and stretchable products for variable products, as an example, are we also working on. So, to sum up here, LightOn have been one of the leaders in the development in printed antennas in smartphone applications, and now we have products running in mass production. Aerosol jet is a cost-efficient option for mass production of 3D printed electronics. LightOn Mobile Mechanical is a viable contract manufacturing source for mass production in this field. LightOn has been leading the development of 3D printed antennas and sensors for over 5 years. We have been successfully deployed and currently using 3DP in mass production. Our 3DP enables unique solutions and give great benefits for our customers. So we have the increased design flexibility, antennas and traces basically anywhere. We have been able to maximize the development speed, which means shorter time to market. We have been minimizing the product total cost, so we have an attractive pricing for this technology, as well as we have been reducing the environmental impact. So we, together with our customers, sees printing of functional traces, antennas, and sensors as a future strategic direction for for production of smart devices and phones. So that concludes my part of the presentation, and I leave the word back to Dave.
Well, thank you very much, Mike and Henrik. We're going to take some questions now. By the way, before we go any further, you can download the slides. We'll ask that. If you send a question in, we will tell you how you can do that. Certainly you can do that after the webinar as well. All right, for our first question, let's see. Oh, there was a quick question on page 17. What does LDS stand for? Henrik, I think that might be yours.
Yeah, so LDS stands for laser direct sintering, and I think Mike mentioned it briefly. It's basically a laser-based technology where you have a special resin which has additive inside, and then you have a laser which basically activates certain traces on the plastic, and after that you go for a plating process to plate the areas where you have laser activated. So it stands for laser direct structuring.
Okay. Here's another one for you. Let's ask, what are the typical failure modes for these printed parts?
In our production, the failure modes, I mean, we have 100% test of the antennas. And antennas, the performance of the antenna is much affected by dimension of the part. So print accuracy and the tolerances in the process is extremely important. That's one failure mode. Also, the process is, we need to monitor the process carefully when it comes to a consistent line thickness. So we need to ensure that we have the same trace thickness all over the part.
Okay.
Yeah.
Mike, here's one for you. Which material companies are supplying ink, dielectrics, adhesives, etc. for the aerosol jet process?
So we work with a wide variety of material vendors, companies like Henkel, Heraeus, Sun Chemical, Peru from Korea. I mean, there's a list of probably 20 to 30 different companies that are supplying various materials, whether it's, noble metals, dielectrics. And there's a lot of newer companies that are, looking at next generation materials. Creative Materials is a company based in Massachusetts, and they develop a wide variety of materials for stretchable and conductive epoxy type materials. So once again, we work with global partners as well as emerging companies as they develop next generation materials to address the next generation set of manufacturing requirements.
Okay, here's a question someone asked. Can you print using gold?
The answer is yes. We have two different types of what we call atomizers. Gold, of course, is a very precious metal, but yes, we can print with gold. We can print with as small amount as 1 milliliter of material. So the answer is yes, we can print with gold.
Okay. And along the line of questions about materials, do you think there might be an interest in using silver-coated copper powder for the ink?
The best way to describe it is, we're a printing company. We're really driven by our customers. Companies like LightOn Mobile approach us and say, hey, that's great. You've been printing silver. We'd like you to print copper. We have people that want us to print materials such as Constantan, which is an alloy. if there's a call for it, the answer would be sure. I haven't heard anyone ask about that, maybe because we haven't seen any of the material available, but if it's a material that we can fit into our process envelope, then we can test and deposit it, and then we can determine whether there's a marketplace for it.
Okay. Well, let's do this way. But what is the maximum print speed in area per second, and is there a theoretical limit?
That's a great question, and we so it depends on what's the thickness of the material that you want to put down. It depends on the width of the material. It really depends on a lot of variables. Most of our customers are printing 20 millimeters or less per second. We've got a couple of customers that are printing up to about 100 millimeters a second, but they're putting down very thin layers of material. Typically, they're putting down 500 nanometers or less of material at those speeds. So once again, I mean, theoretically, our systems, it depends on the automation we're in, but the systems we sell theoretically can print up to a meter a second. But as I said, most of our customers are printing, at less than 20 millimeters a second for the devices they're working on.
What are the number of units per minute per printer can be printed of these phones, these phone antennas?
So for our system, as I said, we have four head systems, meaning that we print four parts at the same time, basically at one production cycle. And the cycle time of these is very much given by the type of antenna we are printing. It could be as low as 10 seconds to produce four parts, but it could also be several minutes depending on the shape of the antenna we are printing. So it's very product depending, I would say.
All right. Someone asked about the drying of 3D. Considering the complexity of 3D shapes, are the drying ovens custom per application or universal?
We typically so at least from Henrik, you can talk specifically about the antennas, but I can tell you that the vast majority of our customers are using standard drying ovens. When we do print materials such as copper, sometimes you need an oven that you can put a forming gas in the oven so that you don't get oxidation of the copper. We also have customers that use lasers to actually sinter the material onto the substrate itself. We have people that use photonic curing, and we have people that actually will use UV curing depending upon the materials. So there's a wide variety of solutions that are available for curing the material. In the case of LightOn, Henrik, why don't you answer that question? That'd be great. What do you use?
Yeah, sure. I mean, we use oven sintering, and for it doesn't really change so much if it's a complex 3D shape or a simple shape. But we are also we have done also alternative sintering such as Xeon-based and these kind of things, at least for test purposes.
All right. Do you see a cost savings in terms of material consumption?
Sorry, could you repeat the question, please?
Oh, sure. Do you see a cost savings in terms of material consumption and actual material cost?
The one major cost saving we see by using this technology is that we can use standard resin. As I mentioned, we are comparing this a lot to LDS, and LDS requires an additive in the resin, which means it's a specially developed resin just for the LDS process. So we definitely see a material cost cost advantage using this technology, since we can print on any generic kind of engineering plastic.
All right. All right, so here's a question for Henrik. How will the movement of mobile networks to 5G affect the printed antenna work that you are pursuing?
I think the printed antennas will probably have a very good place for the 5G type of antenna. So 5G, which is coming now, mostly means going up in frequency, meaning physically smaller antennas, meaning several small antennas into one device. The ability of placing the antenna freely anywhere in the device is a great advantage for this technology, and could be utilized definitely for 5G applications.
So we have a couple questions here on nano inks. Are the majority of the inks nanoparticle based?
For noble metals, the answer is yes. We do have some flake-based materials we print that we find in materials such as conductive epoxy or stretchable materials. But typically the flakes are relatively small. They're typically less than 2 microns. For the vast majority of our conductive work that we do, it really is all nanoparticle-based materials. And that's primarily driven by the desire of many consumer electronics manufacturers to get to much lower temperature materials such as PC, ABS. And the only way we seem to be able to reach the temperatures and get to the kind of resistivity values that customers are looking for, which are typically 2 to 4x resistivity over the base value of the material or the ink, is to get small nanoparticles, such as particles below 10 nanometers in size.
Here's another one. At full ramp up, what could be your theoretical max throughput in terms of parts per month?
This is a bit related to the question before, I would say. So it's very much depending on the shape and size of the antenna. It could be, as I said, the cycle time of the system actually varies quite a lot. It could be 10 seconds. It could be 2 minutes. So it's really difficult to give a generic answer on that one. It depends on the application.
Okay. Mike, here's one for you. How many systems do you have installed worldwide?
We've been selling our products since 2004. Primarily, we had sold into the research and development market up until about 2012, and that's when we started to see more corporate interest in our systems. And we've got well over 300 systems installed worldwide. The vast, I wouldn't say, probably 75% of those systems are research and development, and the remaining 25% are used in from everything from low to high volume production today.
All right. Henrik, are these phones on the market?
Yes, some of these applications I've shown are in the market, but unfortunately I cannot tell any brand name or model name due to NDA. Yeah.
I understand that. Let me ask you this one. This came in. How is the connection made to the via hull? Can one solder to the vias? Am I pronouncing that right?
Well, normally the via hull is just used to connect the top side of the part to the bottom side of the part, and then the connection part coming from the PCB or the engine of the phone is normally like what is called a pogo pin or a spring leaf contact or something like that. We have not really a solution of a soldered connection yet.
All right, and here's another one. Can you elaborate on the capillary action of the substrate that you mentioned as a technological challenge?
Yeah, to some extent at least. I mean, we found during development that when we have a plastic part or a substrate which have holes and voids, we see that when ink adds up into the holes, it actually pulls down the wet ink into the holes, which means that the remaining ink on the top surface is too thin to get the needed conductivity. So it means that a molded structure needs to have a smooth and uniform surface we are printing on.
Okay. Mike, I guess both of you, Mike and Henrik, what advantages and disadvantages of aerosol technology compared to inkjet printing?
That's a tough question to answer. You know, I usually leave that up to the customers. What I can tell you is the strength of our technology is that we put out a lot more material per pass. So, you know, if we're printing a 5-micron thick line across the surface of the substrate with a single pass at 20 millimeters a second, it could take inkjet multiple passes to do that. Another strength of our technology is because of our what we call sheath gas, basically the curtain that surrounds the nozzle. We very rarely have fouling of the nozzle, which is a common problem with inkjet, where the piezos get plugged up with material pretty rapidly, and you need to then start firing out of another hole. Where our system will love to work on a continuous fashion, meaning we're a continuous flow system, so we can print for hours at a time without any interruption to the process. Other key features, our ability to print on three-dimensional substrates. I mean, when you think about inkjet, you've got to be within a millimeter of the surface of the substrate. When you think about aerosol jet, you can be anywhere up to 5 millimeters away from the surface. That allows us to print up and over undulations, both in concave and convex surfaces, things that are extremely difficult with inkjet today. So those are some of the advantages we think we have over inkjet. But we also believe, we're complementary to inkjet technology. We typically don't see us being competitive directly. We see us filling holes where inkjet may not have some strengths, and vice versa. So that's how we view the technologies today.
Here's the question. Do you consider this truly 3D printing or 2.5D printing? And then what is the roadmap for 3D structures?
So unlike 3D printing, this is a terminology issue. So when people think about 3D printing, they really think about solutions from companies like Stratasys and 3D Systems, where you're actually really doing a 2.5D print. With Aerosol Jet, we sell 5-axis of motion systems. What LightOn Mobile has is full 5-axis of motion systems, which means that we are printing onto. We're not creating the substrate. We're printing onto a substrate in 3D space. We're printing on all of the sides of the substrate, the front, the back, the sides, the tops. We're printing into, vias. So we are truly moving in 5-axis of motion, printing in true 3-dimensional space. So that's available today. That's exactly what LightOn Mobile uses today. We can have a full 5-axis of motion. You can have 3+2, 4+1. It all depends on what your part looks like and the requirements you need. But as of the last 2 years, full 3D motion in a production setting has been available day in and day out.
All right, thank you. I have a few more questions for you.
Okay.
Sorry. Is there any?
I'm sorry, Dave, we can't hear you. Dave, you seem to be breaking up. We can't hear you.
I'll try one more time. Is there any data of electron mobility for metals with respect to curing temperatures?
So from Optomec, the answer is we have lots of data, much data. We are just trying to find a material that would work on a low temperature substrate. We work with approximately 20 different suppliers of silver material, probably 120 plus formulations of that material. We tested that material out at various temperatures to find out, what did the resistivity look like over given periods of time. So we have tons of data relative to that. Unfortunately, it's all under non-disclosure with the companies that we work with. They certainly don't want their information out there from a competitive point of view. So, but I can say that we have a lot of detailed information internally relative to the mobility numbers associated with various noble metals, if you will.
All right. Along those lines, two more questions. What kind of environmental qualification have you done on the inks that you're printing?
So let me talk about from Optomec's perspective, and I think this will cover Henrik's perspective as well. So, in this case, we're talking specifically about printing onto mobile devices, printing antennas for smartphones. And in that case, we've done lots and lots of environmental testing, and it all is customer dependent. There's not a lot of standards out there. I think each vendor creates their own standards, but as Henrik alluded to, we do everything from printing onto the surface of a substrate, doing a cross-cut tape to see whether the material is going to adhere as printed, running it through heat and humidity tests, which can last for typically, a few days to multiple days, 10 days of, 80 kind of heat and humidity tests, to salt spray tests where we spray the material with salt water and then we run it through humidity tests, or we continually spray it with salt water and continually run it through humidity simultaneously. And then lastly, we come with cross-cut tapes to see whether the material is still going to adhere, and then we do performance testing. And typically we leave that to our customers to do the performance testing. But before as we try to qualify inks for these various antenna opportunities, we're doing a lot of internal testing of the various materials we get from third-party vendors. Now, subsequent to that, we also are working in other markets, such as printing up the sidewalls of stacked die and printing into 3D advanced packaging solutions, and they all have their own sets of qualifications. A lot of it's mil-aero qualifications, doing BHAS tests and other tests such as heat and humidity.
All right. I want to ask one last question. Is it possible to manufacture an array of aerosol jets in a more compact form than what is shown as the four-head system?
It depends on what you're trying to do. I mean, we typically are a single nozzle solution where we can stack our heads together. There's the distance between each nozzle would be, probably I think it's about 5 millimeters between, maybe a little bit further than that, maybe 10 millimeters between each nozzle. We could put them closer together. The way that you're seeing the system at LightOn Mobile is what you're seeing here is because they want to print a variety of parts. Not only are they printing on, smartphone devices, but they want to print on other devices such as tablets and potentially notebooks. So the heads are spaced a little bit further apart to be able to accommodate those kinds of things.
All right. Well, that concludes our webinar. I want to thank our audience for all the good questions and for joining us. I'd very much like to thank Mike and Henrik for all their help and for doing a tremendous job. The slides, again, will be available. You can send in a question to find how you can get them. And I want to wish everybody a good day.